We now start off with question number 14. A small coil C with n is equal to 200 turns is mounted on one end of a balance beam and introduced between the poles of an electromagnet as shown in the figure. Cross-sectional area of coil is S, length of arm OA is I. When there is no current in the coil, the balance is in equilibrium. On passing a current of I, the equilibrium is disturbed and has to be restored by putting an additional counterweight of M on the balance span. Find the magnetic field on the spot where the coil is located. Can you tell us the approach by which we'll go about solving this question?
Yes, and if we read this question, then it appears a lot complicated. But we just have to find out where we have to work on this.
Right.
So it's basically a balance of torques. One torque is the coil also has a particular mass.
Correct.
And this particular pan out here has a mass.
Right.
So initially they are both balanced by the particular masses.
All right.
Now when we switch on the current, then what happens is that particular M, that is to say magnetic moment is formed. Because of that, a torque is acted upon this whole apparatus.
Okay.
And so to counterbalance that torque, to keep this coil and pan in equilibrium, we have to add an additional mass M.
All right.
So we
are changing the torque, and as a result of which we need some more mass to balance it.
Yes.
Right.
We are just by switching on the current, we create a torque by the magnetic field,
G,
which was not there before.
Okay.
And to balance that, we need a particular extra mass M.
Correct.
So it's just about balancing the extra torque we have, because the previous ones were already balanced.
Right.
So we just work upon the torque. So torque due to the current is equals to M vector cross B vector,
G,
equals N, which is the number of coils, into I into the surface area into B.
Right.
This is the torque due to the current.
Correct.
And then torque due to weight will be equal to L, which is the length of OA, into M into G, basically R cross F. So this is the F, this is R, which is equal to L.
Alright.
We just have to equate these two.
G.
So N I S B, we equate them because this is the extra torque and this is how it is balanced.
Correct.
Equals L into M into G. So basically we have to find the magnetic field. B will be equal to L into M into G divided by N into I into S. We can replace N by 200 as it is given in the question.
Right.
Now if in this question it is asked that where is basically what is the direction of the magnetic moment?
All right.
That would be an interesting question.
Okay.
Now let's see. If we consider O as our reference point.
Right.
So basically we have O here. If we consider the torque about O.
Okay,
so this is our apparatus. We just divide it. Here is the coil and here is the pan. This is the point of suspension.
Right.
Basically. We consider the torque about O.
Alright.
So we consider it to be in this plane itself.
Ji haan.
So R is here, R cross F. So if we do this, it will go into the plane.
Okay.
So torque due to this is going into the plane.
G.
Now since the total torque must be 0, the torque which comes because of this
right
should be out of the plane.
Okay.
And when can that happen? See, the magnetic field is from north to south. And if we have a magnetic moment in this direction, torque equals M cross B.
Right.
So M cross B, it will basically keep your fingers align on M and tilt them toward B, so the thumb will point out of the plane. This comes out, this gives us the direction of torque to be out of the plane of the paper. So basically this was inside and this gives outside.
I'm sorry, but when you look at M cross B, it should be going in, right?
No.
Okay, sure.
So yeah, basically just keep your fingers aligned with M.
Okay, B is downwards here.
And B is downwards.
Oh, okay, yeah, sorry.
So you tilt the fingers downwards and
Yes.
the thumb will point upwards.
Yes, and that's correct. Right.
So we get basically the M value of M to be on the left side of our plane.
Right.
So that is it. We can simplify it. L cross M cross G divided by 200 into I into S.
Okay. So that was question number 14 for us, where we are given a coil with 200 turns and it's placed on the end of a balance beam and introduced between the poles of an electromagnet. And when there is no current in the coil, the balance is in equilibrium. On passing a current I, the equilibrium is disturbed, and we put some more weight on the balance band to restore the equilibrium. So we have to find the magnetic field on the spot where the coil is located. First we start off with the finding out the torque due to the current, right?
Yes.
And then we find out the torque due to the weight and balance both of these, and on equating these we find the answer for the magnetic field, which comes out to be L into M into G upon 200 into I into S. And then we touched upon a very interesting concept where we could find the direction of the
magnetic moment.
Right. So
basically there is one more thing that can be asked, like instead of the direction of magnetic moment,
right,
one can be asked indirectly, like if you have a point O here,
okay,
and you view this from O, like
right,
you view the coil from O,
okay,
then what will be the direction of the current? Will it be anti-clockwise or will it be clockwise? So that would be an interesting question.
Okay.
Now if we look from here, the magnetic moment comes out to be here.
Okay.
So basically on looking from O, if it is in anti-clockwise direction,
right,
like just see, let's just consider ourselves in the plane of the paper. The coil is in the plane of the paper.
Ji haan.
And above it there is the point O.
Ji.
So if from O we look downwards and we see this anti-clockwise current,
Ji.
then we can safely say that the magnetic moment will be coming towards us.
Right.
By the right hand rule.
All right.
So basically if we look from O, then the magnetic moment should be coming here, that is towards us.
All right.
Hence if we look from O, the direction would be anti-clockwise.
Right. Correct. So that was question number 14. We now move on to question number 15. Two long thin parallel conductors of the shape shown in the figure carry direct currents I1 and I2. The separation between the conductors is A. The width of the right hand conductor is B. With both conductors lying in one plane, find the magnetic interaction force between them reduced to a unit of their length. So can you please explain this question to me a bit? This sounds a bit complicated.
Yes, basically see, this is I1, it carries a current I1, and this conductor carries a current I2.
Right.
We have to find the force of interaction between them, or basically the force per unit length between them. Now the difficulty lies in the fact that I2 is not just a single wire. For a single wire we had the formula mu naught I1 I2 by 2 pi into the distance between them.
Ji haan.
But this is basically broad, and the current is divided. The current is carried by a width B.
Alright, so this is like a plain sheet, is it?
Yes, it is just a sheet carrying the current.
Okay, so the whole sheet is carrying a current I2 as it goes through it, right?
So basically for this, like the force, we have to find the force on each particular element
within the sheet.
Yeah, we just say the sheet is composed of a large number of wires,
right,
each of length dr.
Okay.
and we find the force on each of those wires of length dr,
Right.
and then we just sum them up to
Okay.
get the net force per unit length.
And this will go on with integration, is it?
Yes.
All right.
So let's start with our integration. This is one wire, and let's say we consider this wire
Right.
at a distance r
All right.
and with width dr.
Right.
So basically this small thing, the small width dr, we are considering to be a whole wire.
Okay.
Now we know the formula for the force of interaction between two wires, two infinite wires,
Right.
and this is one infinite wire and this is another one infinite wire.
Right.
So basically the current carried by dr would be dr by b whole into I2. This is just by the unitary method we can say, because b length carries a current I2.
Right. Right.
So one unit carries I2 by b, and so dr will carry dr into I2 by b.
Right.
This was I1. Okay, so this is the current. Now let's go to the force. dF equals, as we saw for two wires, mu naught I1 I2 by 2 pi into the distance between them.
Right.
In this case it equals mu naught, this is I1 by 2 pi, the d is the distance is r,
Right.
and I2 is dr I2 divided by b.
All right.
Now see, these wires start from here,
Okay.
from this, and end till here.
Okay.
So basically the value of r will vary from a
To B.
to a plus
Okay.
a plus b.
Right,
So
a
this
plus
is the
b.
width b.
Correct.
So it will vary from a to a plus b.
Right.
So if we have to integrate df equals integral r varies from a to
A plus
a
B.
plus b. Okay, mu naught I1 I2 by 2 pi b. Yes, it's okay. 2 pi b dr by r.
Right.
Basically these are all constants, so dr by r is ln r, so we can just write down the answer directly. Mu naught I1 I2 by 2 pi b ln of a plus b divided by b.
Right.
This is
Correct.
the final answer.
Right.
So this is basically the answer for a force of interaction between them. Now one thing is interesting to see here. Now we see that B is the width of the second conductor. Okay.
Right.
So if B tends to 0,
Okay.
like we make B very small as we had considered it for, so that would just equal the case that another wire is kept there.
Right.
If B tends to 0. So now we see whether that mathematically comes out to be true or not.
All right.
Because mathematically we should then get this particular formula, mu naught I1 I2 by 2 pi d.
Right.
So like mu naught, we find limit b tends to 0 for our force.
Okay.
These are all constants like mu naught I1 I2 by 2 pi. We don't need to consider them because they come out of the limit.
Right.
We just need to find the limit for limit b tends to 0 ln sorry, this should be a plus b divide by A, because the lower limit was A.
Right.
So this is ln of A plus B divided by A. A plus B by A whole divided by B. So this comes out to be 0 by 0 form by L'Hopital rule. We find that we differentiate it, so it will come out to be ln of 1 plus B by A whole into 1 by A, this whole divided by 1. So when we see this, this actually comes out to be 1 by A, and if we keep it here, mu naught I1 I2 by 2 pi A, as we had expected.
Right. So that was question number 15 for us, where we had to find the force of interaction between the two thin parallel conductors. We take the first conductor carrying I1 and we look at the second conductor as a whole sheet carrying a current of I2, and we divide it into very thin strips of
with dr,
and we find the force of interaction between those strips and the element carrying current I1, and which, when we start off with the integration for this, we get the force of interaction dF as mu naught I1 by 2 pi r dr I2 by B, and we integrate between the limits A to A plus B, and we get our answer as F is equal to mu naught I1 I2 by 2 pi B log A plus B by A. Right?
Yes.
And then we try to look at the limits for B heading to 0.
So this implies that this is just the same as we keep another wire at a distance A to the wire carrying current I1.
Right. So that was question number 15. We come to the final question of this chapter, question number 16. Two large metal sheets carry surface currents as shown in the figure. The current through a strip of width dl is kdl, where k is a constant. We have to find the magnitude of the magnetic field at points P, Q and R. Right. So can you tell us how we start off and proceeding with this question?
Yes, basically for this question we find out the magnetic field by the method of superposition.
All right.
That is to say that the magnetic field at any point P, Q or R would be the summation of the magnetic field by this sheet and this particular sheet.
Right.
So let's see how to proceed in this. Basically, let's see that if we can find out the magnetic field by one particular sheet above and below it, then we can find the magnetic field by both of them by just combining the results.
Okay.
So let's consider a big sheet. Suppose it carries current out of the plane. Now see, this is a large sheet, a large metal sheet. Large in this question implies that it is sufficiently large to justify a case of symmetry, which is to say that the field lines will be parallel.
Okay.
Now how do we get this, or how do we intuitively get this? So let's just say if there are two loops,
okay,
like basically these are two coils, this is coming back and this is coming back again. So because of this, the magnetic field here, because of this it would be somewhere around here, and because of this it would be here. The resultant would be here when this point is symmetrically placed with respect to these two coils.
Right.
Okay. Now if there are three, this is just current coming out, and we are looking here at the top of this. Like if we look at from the top, it looks like this, because these are the curls.
Right.
And we are finding the magnetic field because of this, all this.
Okay.
Because of this, if we have a point kept here, this will give magnetic field here. Because of this it will come here. Because of this it will come here. The resultant will again come here. So we see that when the point is taken symmetrical with respect to the three basically turns, then it comes out to be parallel.
Right.
Now since this is very large, so any point we take, for that we can divide it into two symmetrical halves, because
Right.
this extends almost till infinity on both the parts.
Okay.
So because of that we can now safely say that the magnetic field will be parallel here
Right.
and here. Throughout it will be parallel.
Right.
Now how do we proceed about finding the value of the magnetic field? So for that we have a law which states that closed integral of b dot dl b vector dot dl vector is equals mu naught I. Okay,
Right.
so let's basically take one particular sheet, and for that we'll solve it. It is coming out of the current is coming out of the plane. We select a random path. Denoted by A, B, C, D, and we move in this direction. So for
Right.
this direction, as we had seen in the theory part,
G.
the I will be, because the thumb is pointing towards the I, coming towards us, so I will be taken positive.
Right.
Now let's say this length is L. Okay,
Okay.
we start finding surface integral of B dot dl vector. We divide this into four parts.
Okay.
For CD, for DA, for AB, for BC. This is integral B into DL. Okay. For CD and AB, the value of B would be same because it is completely symmetrical.
Right.
Okay, because this is just one sheet here,
Right.
and up or below,
Okay.
just change in direction, the magnitude would be the same.
Okay.
So for CD, we would have B into L, plus for DA, see, B is here, and for our purpose, DA vector is here.
Right.
So B vector dot DA vector comes out to be 0.
Okay.
0 plus AB is again B into L, plus BC again 0, because that is perpendicular.
Okay, so we're looking at the dot product, and because
yes.
they're perpendicular, they both add to 0.
Yeah, exactly. Now we say mu naught into I. Now how do we find I for this particular length L?
G.
Just look back at the question. We see that for a strip of it DL, the current is KDL.
Okay.
Means it is linearly proportional. We just
Right.
multiply the length and we get by K, and we get the current.
Right.
So the current comes out to be mu naught whole into L whole into K.
Okay.
Okay, so B here is mu naught K divided by 2.
Right.
Now this is because of one sheet. Okay, this is just because of one sheet. The B here and here is mu naught K by 2.
G.
So for our case, we just add these up because of one sheet. Because of P, the magnetic field, because of this sheet, the magnetic field at P would be here, and because of this, it would be here. Both
Okay.
mu naught K by 2, so they will
Okay.
cancel each other,
Okay.
come out to be 0.
Okay.
Same goes for R.
Right.
Why-
So on the outer regions of the sheet that are exposed beyond
Yes,
the boundaries,
beyond
of
the boundaries of the large plane sheets.
right, the magnitude of the
magnetic
field is
fields are
equal
0.
and opposite, and as a result of superposition, they cancel out and they come out to be 0. Right.
While inside the case is different. Inside both are in the same direction because of this and this. So
Right.
basically they add up
Okay.
to give us mu naught K.
Right. So
Yeah, so this is basically mu naught K by 2 because of this it's mu naught K by 2 here,
okay.
and then because of this it's mu naught K by 2 here.
Right.
So this basically adds up to give us mu naught K as the net field.
Okay. So for solving this question, we have to look at the integral of the field B dot dl
Yes.
right? And we have two infinitely large sheets, as a result of which, when we are looking at the field in consideration at points P, Q and R, because the points P and R are outside the regions, and the field acting on the regions P and R due to both the sheets are equal and opposite in direction, they add up to
Yes.
0, right?
And I would like to tell that in this particular question there were 3 key points. First was basically a realization that we could do it by superposition
Right.
of 2 sheets.
Right.
We thought of this particular principle because there were 2 sheets both exactly in the same way,
Right.
but just the current directions were different.
Right.
So basically superposition.
All right.
Second, using the symmetry to basically induce or deduct that these fields will be parallel.
Right.
And third was integral BDL, and using the correct path for it. Like, it would have been very hard had we chosen a path like this, say a circular path.
Okay. Right.
So basically we choose the rectangular path and it becomes very easy for us to calculate it.
Okay, so that's question number 16, where we had to find the magnitude of magnetic field at points P, Q and R, and we get the answer for the magnetic field at points P and R as 0 and at point Q as mu naught K.